Welcome to EC&M Tech Talks. This is a series of how-to videos where we cover everything from basic theory to the electrical codes and standards that govern our installations and equipment to the distributions and systems themselves that we find out in the field. So anyway, welcome. This video, Tech Talk video is brought to you by EC&M Magazine, Electrical Construction and Maintenance Magazine. If you haven't already, you need to go to ecmweb.com. That's ecmweb.com. And look in the upper left-hand corner, there'll be a drop-down menu. And click on that first line there that says premium content. Go ahead and sign up for that premium content. It's free, and you'll have access to tons of information about the different topics that we talk about on Tech Talk, as well as other articles and videos and webinars and so forth. So anyway, make sure you do that. I'm Randy Barnett. I'm your host today for this Tech Talk, where we're going to talk about electric shock. You know, all familiar with Crescent tools, of course. And this Tech Talk today is sponsored by Crescent. They have a history of more than 100 years of performance, quality, innovation. Crescent is holding true to the fundamentals that make it one of the most trusted names in hand tools and storage worldwide. It consistently delivers products that exceed customer expectations for quality, durability, performance, and value. And the good news and what pertains to today's talk is that Crescent has a new patented isolated technology called eShock Guard. It's designed to protect you from electric shock, and that's what we're talking about. So anyway, it provides insulation of all standard bits in our drills up to 1,000 volts. Trusted by the trade, Crescent's eShock Guard stands between you and 1,000 volts. So we're going to talk about this little guy today, and we're going to see why it's important and how it can help to save you from electric shock and even something worse than that, electrical fatality. We don't ever want to be involved in anything like that, certainly. So anyway, we'll be discussing this a little bit later on. First of all, what is electric shock? We all understand that if I touch something I shouldn't, and the current flows from the live energized part through my body and into the earth, it will travel through the ground and back into the grounded electrode conductor and on back to our transformer for complete path of current flow. So the current's happy. It gets to go back to where it came from. Unfortunately, if it goes through our body, that's bad news for us, isn't it? And you see, current doesn't care. It doesn't care what we do. It doesn't care if we're a first-year apprentice, a seasoned veteran journeyman, a 35-year master electrician, or if we've got our master's in electrical engineering and have that PE designation behind our name and so forth. It just doesn't care. If it wants to go through your body and has the opportunity, it's going to go. So we want to talk about today how we can protect ourselves from that happening to us. Now, the numbers, you know, if you look at the numbers, how much current does it take to shock us and so forth? And one of the concepts is if I grab a hold of something at about 10 thousandths of an amp of current flow, that's 10,000, that's 10 milliamps of current flow. That's enough current flow to cause my muscles to contract to where I can't let go. And of course, the result of that, if I can't let go, could be a fatality, because by the time I get up to about 75 milliamps, my heart can go into ventricular fibrillation, where it beats erratically, sort of like a pump that cavitates, right? It doesn't get, the pump that cavitates can't get proper flow through it. And if my heart is beating erratically, it can no longer deliver that blood flow that it needs to. So anyway, by the time I get up to probably a 1/10 of an amp, something like that, they tell us a 1/10 of an amp for 2 seconds, I'll end up being a fatality. And that's very quick. I mean, just boom, that quick and it's over with, doesn't it? So we have to see how to protect ourselves before something like that happens. And that's what we're going to talk about today. Where do those numbers come from? There was a Dr. Charles Dalziel several years ago, many years ago, who did some studies, and maybe you've seen some of his videos and whatnot. But also we rely on the NFPA 70E. An informative Annex A of the NFPA 70E standard, there's the reference to the IEC standard that tells us how much current the human body can handle. Back in informative Annex A of NFPA 70E, and the publication is the IEC TS 60479-1, effects of current on human beings and livestock. So anyway, you can find out more on those numbers if you need them. But the bottom line is we just need to go out and work and protect ourselves out in the field. That's what we want to do. Right? So let's take a look at how we can do that. Probably, you know, in the best way, right here, isn't it? Lockout, tagout. Create an electrically safe work condition. Lock out and tag out the circuit, the equipment, and make sure it's de-energized. And that includes all sources of power, capacitors discharged, and so forth. So anyway, in NFPA 70E Article 120, that gives us the 8 steps in order to create an electrically safe work condition. So lockout, tag out is always the best way to go. However, in the real world, lots of times we don't lock out and tag out, do we? Why? Because we're doing something like troubleshooting or voltage testing, or we may even have to do some repair work inside of some energized equipment and so forth. So that's where all of our safety rules for NFPA 70E come into play. Now, one of the requirements of NFPA 70E, it talks about PPE. So for instance, for shock protection, what do we have for personal protective equipment? And that's our insulated rubber goods. So our insulated rubber gloves, for example. And that's my last line of defense. I would never put this on my hand and say, I can go back here and touch this energized circuit and it can't hurt me because I got on my rubber glove. That would be crazy. That would be insane. So we would never do that. The only reason that I wear my rubber glove is in case I'm in here doing something and I accidentally touch something I shouldn't, I don't get myself shot. So that's a good thing. Now, rubber gloves, they have to be tested and inspected daily before each use. If you don't know how to do that, then you need to get some training on that, because we have to check the dates, we have to check the fit, we have to check the cleanliness, we have to do an air test on it and so forth, as well as check the leather protectors. So that's a good topic for a safety meeting for you right there, is to have someone go through and how to do a test on a rubber glove then. Insulated tools. Let's talk a little bit about insulated tools. This screwdriver right here has a rubber handle on it, good quality screwdriver, no problems. However, it says on here it's not good for protection from electrical shock. Heck no. I mean, yeah, that's rubber and that protects me, but how much? I don't know. It's not rated. What I'm looking for is maybe on a screwdriver, I'm looking for something that has a double triangle on it, one triangle inside of the other. And that tells me that my tool has been tested to 1,000 volts and meets the standard for being an insulated tool. GFCI protection is another way that we can protect ourselves from electrical shock. Ground fault circuit interrupters, GFCIs then. When we think of GFCI protection, we probably think a lot about Article 210 of the National Electrical Code on branch circuits, and specifically 210.8 on ground fault protection for personnel, our GFCIs then. Section A is for dwelling units, and Section B of 210.8 is for other than dwelling units, and then there are other sections after that. But anyway, that tells us where we need to install our ground fault circuit interrupters in our premises wiring systems. But there's another place that we use GFCIs a lot, and that's if we take a look in the National Electrical Code, and once again, I'm using the current 2020 edition. If we take a look at Article 590, and by the way, there are many, many other requirements for GFCIs. In fact, we've mentioned that before in previous tech talks within the National Electrical Code. But anyway, if we take a look at Article 590, Article 590 of the NEC is on temporary installations. And specifically, 590.1 tells us the scope of what this applies to. And it applies to temporary electric power and lighting installations. And it goes on in the next section and talks about all wiring installations. And it goes on and gets into more detail. And basically what it says is that we're going to do any installation, construction, maintenance, remodeling, demolition, whatever. We're going to use temporary wiring for that. we still got to meet all the requirements of the first 4 chapters. However, this one article 590 can take and we can modify those first 4 chapters and apply the rules of article 590. For example, if I'm going to use receptacles, 590.6 talks about, 590.6, ground fault protection for personnel. And it talks about GFCI protection for receptacles. And what it boils down to is anytime I'm going to use a receptacle, whether it's a temporary receptacle I've made up for this particular project, or if I'm using the receptacles that are part of the premises wiring of the building, if I'm going to use those receptacles in order to supply me with temporary power while I'm doing some work out there, those receptacles have to be GFCI protected. Now, make sure you read Article 590 in your code because there are exceptions. Also, you want to take a look at your requirements in 590.6 B for GFCI protection. And the alternative to use the Assured Equipment Grounding Conductor Program. Now, the Assured Equipment Grounding Conductor Program is covered in the NEC, as I mentioned in 590.6B, where we are now. And it's also covered in OSHA. So OSHA is, of course, our real driving force for the Assured Equipment Grounding Conductor programs. And basically what that program says that every 90 days, I'm going to go out and I'm going to check the continuity of my equipment grounding conductors from the metal frame of the equipment back to the grounding prong on my plug. But take a look at this one. Somebody's pulled the grounding prong out, huh? And that was probably pretty common many years ago. But anyway, now we use a lot of battery operated portable power tools and so forth. But we were required to go through and every 90 days and check this on our extension cords and portable tools and so forth. And we have to have a written program in place and somebody designated to be in charge of that program and so forth. So all of the rules, then take a look in NEC Article 590. Okay? 70E, NFPA 70E provides us, of course, a lot of information on shock protection. Section 130.4 says that before we go out and do any job out in the field, that we have to go ahead and do a shock risk assessment. And that shock risk assessment tells us 3 things. We have to come up with 3 things in our shock risk assessment. Number 1, we have to identify the voltage hazards. What is the shock hazard? Well, it might be a 240 volt panel board, a 480 volt controller, or a 4160 volt circuit breaker that we're going out to operate or something like that. So we have to identify whatever those voltage levels are and the potential hazards there. If we take a look in Article 100, it defines a 70E, it defines for us an electrical shock hazard. And an electrical shock hazard is when we're exposed to the energized circuit parts or conductors. Obviously, if this were energized behind me, that would be exposed circuit parts, wouldn't it? Now, a conductor with insulation on it, that's not exposed, it's not an exposed energized conductor, okay? It's insulated conductor, so I'm not exposed to a shock hazard. If you take a look at this panel, up at the top are the barriers for where the main power comes in to go to the main breaker and on the line side. And so I'm protected by that barrier from inadvertent contact. If I'm in here doing something, I don't inadvertently touch the main power terminals coming in to this panel board. So back to our requirements on the shock risk assessment, we identify the hazards. And then the second thing we have to do is say, well, what is the likelihood that I'm going to be injured by this hazard, assuming that I follow safe work practices and wear the appropriate PPE. And then number 3 is, what am I going to do about it? What steps am I going to take in order to mitigate this shock hazard? So the things that I can do, just like we talked about at the beginning of this tech talk, I can create an electrically safe work condition, lockout, tagout. I can wear my insulated rubber goods, my insulated rubber gloves for shock protection. I can use insulated tools as needed for secondary shock protection then. Now, we talked about this isolated bit holder, and we said it was rated for 1,000 volts, and it meets the IEC standards for electric shock protection then. So that's a good thing. 70E also provides us with shock boundaries. So to clear things up, we said just a minute ago, this is a barrier. It prevents inadvertent contact with live energized parts. I can set up a physical barricade that people can't cross to prevent them from getting too close and injuring themselves to whatever it is I'm working on. And then we have boundaries. Boundaries are in my head right here. That's the only place they really exist, you see. So when I go to do work inside of this panel, I have to establish some boundaries. I have to know that my limited approach boundary, in other words, where a shock hazard exists, is at 3 feet 6 inches from a panel board like this, okay? So this is a single phase panel board. And yet in my tables in 70E, it gives me the voltage levels in phase to phase. So what do I have to do? It says, well, take your phase to ground voltage, which would be 120 volts in a 240 panel board, and multiply it times the square root of 3, which it gives you in the 70E standard right beneath the table as 1.732. So if I multiply 1.732 times 120 volts, I get 208 volts. And so that's what the voltage that I would have to use to base my boundaries on. Now, so my limited approach boundary would be 3 feet 6 inches. That's considered to be, as we said, the shock boundary. If I enter that boundary, I'm subject to electric shock because I could reach in and touch something I shouldn't. And then as I get 1 foot away, if I'm only 1 foot away, that's considered to be the restricted approach boundary. And that's based on inadvertent movement primarily, the very small gap, like 30 thousandths of an inch, that an electric arc could possibly jump through the air at that low voltage level, plus my 1 foot of inadvertent movement adder, they call it, where I may be working in the panel and accidentally, look around and touch something I shouldn't or whatever. So anyway, my restricted approach boundary, what that means to me is that anything I take within that restricted approach boundary has to be insulated. So if I'm going to put my hand in there, my hand's going to be insulated, isn't it? By the rubber gloves and leather protector. If I take a screwdriver in there, the screwdriver is going to be an insulated screwdriver. Let's talk about this tool a little bit then, our isolated bit holder. We said it's rated for 1,000 volts, just like the screwdriver is. So where can we use it? Well, depending on what I'm doing, I may be able to use this inside the restricted approach boundary, but an important part of understanding that table, and that's table it's in 130.4 on shock protection boundaries they have one table for alternating current and one for DC. But it tells me in the AC table, if the voltage is up to 120 volts, that there is no restricted approach boundary. For the restricted approach boundary at 120 volts, it's a void contact. So at 120 volts, I just simply avoid contact. The way this little tool is constructed is there's actually an isolation area between where the bit goes in and the end. By the way, that's a good strong magnet. Tried that out on the bit, and good strong magnet, which we like out in the field, don't we? But anyway, in our bit holders, if not, it's a pain, okay? And then there's an isolation area in here so that the driver end that goes into the drill motor does not even touch the bit down here at the end. So anyway, 1,000 volts of protection. So excellent for 120 volts and below. If you find yourself where you do have to do some type of live work, and consider it for use in a restricted approach boundary, as that can apply depending on the work that you're doing and the type of tools that you're using and so forth. So anyway, great tool. I want to say, don't go home without it, right? Well, make sure you get one from somewhere and go out and purchase one and probably have a couple in your toolbox or something like that. So anyway, good shock protection there. Now, insulated tools. Let's talk about something else. The last step, so there are 8 steps to creating this electrically safe work condition in NFPA 70E. The last step has you to install temporary protective grounds. Normally, we don't do that unless we're working on some medium voltage system or above. Okay? I want to show you what we use, though. This is an example of an insulated tool, and this is a live line tool. This is called a hot stick or shotgun, often referred to. It's got a handle down here, and I can slide the handle back and forth, and as I do, that comes out and opens up on the end, a hook, and I can hook onto something and do some work, okay? Now, the reason I point this out, this is insulated. When this is manufactured, it is insulated at 100,000 volts per foot. That's a lot of insulation. We test it every 2 years now at 75,000 volts per foot. So there are a lot of tools out there that can give us a lot of protection. If you think about it, even our test leads on our meter, the test leads on the meter are insulated to 1,000 volts. So lots of protection out there for us, whether it's, first of all, we want to lock out and tag out. So lots of protection out there from electric shock. Number one rule, lock out and tag out. Create an electrically safe work condition. If I still have to do work on energized equipment, follow all of my safety rules, use my hierarchy of controls, it's called, in the NFPA 70E standard. Wear my insulated rubber gloves, my PPE, to protect me from electric shock. And finally, as that secondary protection as well, use insulated tools that are properly rated. So we'll go ahead and wrap things up because we're out of time for the day. But we want to thank EC&M Magazine, who's part of the Endeavor business portfolio, for putting on this Tech Talk. And certainly we want to thank Crescent for sponsoring our Tech Talk today. We certainly appreciate that. And once again, I'm proud to use their tools in our work. Right? So thank you. Work safely, be safe out there, and we'll see you at the next Tech Talk.